Hello everyone, I am Murchisman Ghosh from Purdue University, and today I will be presenting our recent work of power and electromagnetic side channel attack resilience in 65 nanometer AES-256 exploiting clock-slew dependent variability in CMOS digital circuits. This work is done in collaboration with Intel Labs. This is outline of my presentation. I'll start with brief motivation, then I will discuss about key techniques in detail. Then I will talk about system architecture. Finally, I'll talk about measurement results in detail before summarizing the key outcomes. Let's start with motivation. Mathematically secured cryptographic algorithms leak critical information in terms of electromagnetic radiation, power consumption, timing, cache hits and misses, etc. This side channel analysis attack has reduced time complexity of an attack of an AES-256 from order of 2 to the power 256 to order of 2 to the power 13 and has made it practically possible. Recently, hackers have shown that AES-256 key recovery is possible within just 5 minutes, even from a meter distance. This is a standard side channel analysis attack setup. First, we need to collect electromagnetic or power traces from the encryption engine. Ciphertext is anyway publicly available, and based on that, we can build a Hamming distance model. Then the measured traces can be correlated with Hamming distance model. We can guess key byte with maximum correlation coefficient as correct key byte, and after some time, it matches with actual correct key byte. Hardware security community has represented many countermeasures against this type of side channel analysis. One genre of this countermeasure is called architectural or masking countermeasures. However, this is not generic and it suffers from high overhead. Now, as power side channel attack is mostly carried out through power port or VDD port, it's intuitive to have the protection at VDD port. This type of protection is well explored in circuit community, but it suffers from high V droop and high area overhead. However, this type of solution is very generic in nature. I will briefly talk about some state-of-the-art VDD-based countermeasure against side channel attack. VDD-based countermeasures include buck regulator and series LDO-based solution. This buck regulator and LDO-based solution achieves medium security around 6.8 million to 10 million minimum traces to disclosure against power side channel attack due to loop randomization and frequency randomization. Note that inherently, ideal series LDO-based implementation leaks critical information as LDO current always follows the instantaneous current drawn by the load. Current domain signature attenuation-based solution solves this problem. It attenuates the signature using high output impedance of the current source, which acts as shunt LDO over the encryption engine or over the load. However, when we move it to a digital implementation, attenuation is often reduced, and we should add other countermeasure as time-varying transfer function for higher security. Another genre of countermeasure includes digital nonlinear LDO with arithmetic countermeasure. However, it is high overhead due to LDO, and also arithmetic countermeasures are not generic in nature. Now, a digital design has two ports, one VDD and one clock. And as power side channel attack is carried out through VDD port, it's intuitive to have a countermeasure at VDD port. However, can clock port be of any help? And that is something we are going to explore in this work. Now I will talk about key techniques. When we touch clock port, first question comes to our mind, will timing be violated or will it be okay? Is there any setup or hold violation? Is there any performance trade-off? That is something I'll try to answer first. Now, combinational path delay does not really depend on the clock. It does not change with respect to slew. And that's why there will not be any functional failure due to setup time. Now, hold time increases as you are increasing slew. However, if we remember the hold time constant, hold time should be less than clock to queue delay added by combinational delay. Though hold time is increasing with increasing slew amount, clock to queue delay is also increasing because of slew clock data gets latched later. And in our entire design space, clock to queue delay is always greater than hold time, which makes sure that we do not have any yield failure. However, is everything good? There is no drawback? No, that is too good to be true. As we are using weaker buffer, as we are using slew clock technique, after some frequency, if we want to operate AES at very high frequency, clock port will not be able to reach toggle point. That means at higher frequency, there is possibility of functional failure. However, this can be mitigated by increasing buffer's driving capability. Now we will discuss the effect of clock slew dependent variability as countermeasure. Now, if slew reaches to the flip-flop has some internal buffer, and once slew is getting propagated through those internal buffer, it's getting better and better, but never reaches as good as ideal clock. And due to this, we see uneven duty cycle distortion and slew-dependent latch delay in the circuit, which is aided by amplified Elmore delay and intra-die process variation, which is some measurement features helps against side channel attack. In brief, we present a fully digital generic clock-based countermeasure against power and electromagnetic side channel attack. Note that clock randomization and system level is used for further benefit. Clock randomization is more effective in presence of skewed clock. Now, every flip-flop has two inverter-based buffer in the process we are using, which is 65 nanometer CMOS LP process. When skewed clock propagates through this inverter, it gets better and better. For example, if we see the left side image, in case of ideal 0 to 1 transition, the inverter changes from 1 to 0 instantaneously, because at stage 1, NMOS is in saturation region, and in stage 2, NMOS is in linear region. However, that is not the case when you provide skewed clock. If skewed clock comes, that means at stage 1 or initially NMOS will be in subthreshold saturation region, where current is way lesser than normal saturation region current. And due to that, there will be still slew, there will be more time to reach the stable point. Stage 2 and stage 3 is very similar to stage 1 and stage 2 of ideal case. However, due to the stage 1, slew will still be there. We have simulated few results here. We can see we have named slew at clock port C and Cn as S0, S1, and S2. And we have plotted that slope S1 versus S0 and S2 versus S1. We can see a 4x improvement every time. However, it never becomes ideal. Now, as we are providing slewed clock, toggle point changes and duty cycle gets distorted from 50%. Also, as this slew reaches different clock at slightly different time, it creates uneven duty cycle distortion, which helps against side channel attack. Now, slew-dependent latch delay creates unevenness as well. We see different slew at point C and point Cn. Now, if we talk about the clocked latch circuit, which is there in D flip-flop, high to low latching is based on the point C. However, low to high latching is based on point Cn. As Cn and C has different slew, this latching time of high to low and low to high is different as and now a function of slew. Further, Elmore delay is also amplified. If we provide ideal clock after buffer and at different point like V1, V2, V3, we see some distorted clock. However, initial clock, if initial clock itself is slewed, it's further slewed due to cumulative effect. And this further increases cumulative delay in different flip-flops, enhancing the effect of 1, 2, 3 against side channel attack. Now, due to all these effects, we see a 10x improvement at clock edge variance in 14th cycle pause edge clock, which is the attack point in our case. In red, you can see the sharp clock, but while you are using green or while you are using slewed clock, we can see the 10x improvement in variance, which directly contributes to possible 100x improvement in minimum traces to disclosure. Now, we plot time domain traces or time domain current traces with different 6 plain text here. And note that this is simulated trace, so we have just effect of 1, 2, 3 here. Here we can see power profile is a function of data. However, that 1-to-1 relation is broken when we introduce slew with 100 femtofarad cap. We can see it's not that straightforward anymore. Basically, power profile is now a function of data as well as a function of delay, which is function of slew. This becomes very clear when we further slew it with a bigger cap with 1 picofarad capacitor. Now we can clearly see that different plain text is distinguishable in different way, and it's not just function of data anymore. Now I will talk about system architecture. Our AES 256 follows 128-bit parallel architecture. It has slewed clock generator as well as frequency generator, which randomly creates the frequency before getting slewed by slewed clock generator. We have 128-bit scan chain, which configures plain text every time while we want to attack or while we want to text. This is our clock randomization circuit. It has 2 parts. First part is a fine randomizer circuit, which is made by a tunable stage ring oscillator circuit. And we can switch between number of stages by randomly selecting them using a LFSR. For further randomization, LFSR is seeded by TRNG. We have a quartz randomizer circuit, which is being done a frequency divider by T flip-flop. Again, we can randomly select those quartz randomization circuit, and we can randomly select the frequency this way. Once randomized clock is obtained, that is fed through slewed clock generator circuit. Our slewed clock generator circuit is pretty simple, and it's made of a switch capacitor circuit. We have different load capacitor, and we connect them with the clock port with different switches. And these switches are made of transmission gates. We have multiple level of slew, which we can change if required. However, for this experiment, we are sticking to one particular slew. In general, clock randomization becomes ineffective in presence of time alignment attack or in presence of frequency domain attack. However, when it's aided by clock slewing technique, it becomes far more effective. Post-processing doesn't work very well against it. Now I will talk about measurement results. This is our IC micrograph. Clocking circuit and AES 256 is visible. This IC has been taped out with 65 nanometer CMOS low power technology. Now packaging is normal chip-on board with wire bonding and globe top encapsulation. We operate our IC at 0.8 volt and 10 megahertz, and it consumes around 16 milliwatt power. As a supply decoupling capacitor, we are using 50 picofarad MOSFET. The total area of this circuit is 0.1 millimeter square. We use 387-bit scan chain to configure different configure AES with different plain text and key. We have a clocking circuit which is being operated at 0.72 volt, which takes an active area of only 0.11 millimeter square. Slewed clock draws 627 microamps current to drive an average of 10 megahertz clock. We have 39-bit scan chain to control the clocking circuit. This is our side channel attack setup. Traces are collected using a 5 GSPS oscilloscope. Collected traces has been fed to PC for further processing. PC controls data acquisition card and inputs to the IC. We have an AWG to create clock and enable signal. We have a DC voltage source for powering up the circuit. For EM side channel attack, we use similar approach, but we collect traces using a 10 millimeter H probe and amplify it using a 40 dB amplifier before feeding it to a 5 GSPS oscilloscope and follow the same procedure. This is the result of correlational power attack on slewed AES. We can see that unprotected AES can be hacked with just 11K traces. However, in presence of slewed clock, it takes 1.2 million traces to get the correct key byte. We have explored one attack strategy for clock randomized AES. Note that clock randomized AES in general seems to be working very good. However, it's vulnerable against time alignment attack or frequency domain attack. To demonstrate such an attack, we have collected the trace and we have passed the trace through a bandpass filter with 900 MHz center frequency and 100 MHz band. We have observed all the leaky components stays there. Once we have filtered the traces, we have used correlational power attack or standard correlational EM attack to get the correct key byte. This is power trace of clock randomized AES. The left side, you can see time domain trace of clock randomized one at different frequency. After that, it's filtered and we have zoomed in, and zoomed in version is observed at right side graph. When we carry out correlational power attack on clock randomized AES, it does not reveal any possible key bytes with 270K traces. However, if we convert them to frequency domain and carry out the same attack, we see that there is a peak of peak of correct key byte at 950 megahertz, even within 270K traces. So we decide the filter of center frequency 950 megahertz and 100 megahertz band, and after filtering the trace, we use correlational power attack. And with that, we are able to break clock randomized AES with just 70K traces, which is 5x improvement with respect to unprotected AES. However, when we add it to slewed AES, we see that even after 20 million traces using both time domain or frequency domain CPA, correct key doesn't come out. TVLA-based leakage analysis supports very similar findings. We can see the existence of leaky component for unprotected with just 120 encryptions. However, in presence of slewed clock, we see that it starts to leak with 0.5 million traces. And in presence of both clock randomization and slewed clock, we see there is 40,000x improvement in number of traces to leak meaningful information, which is 6 million individual traces. In brief, unprotected can be broken using a CPA with just 11K traces. Using clock randomization, that is improved by approximately 5x, and minimum traces to disclosure is 70K. Just by using slewed clock, it's almost 100x, which is 1.2 million traces. But when we add both of them together, or both slewed clock and clock randomization together, we see that is working more than multiplicative effect of individual of them. And correct key byte doesn't come out with even 20 million traces. We did the similar experiment for correlational EM attack as well. We see that unprotected AES can be broken with just 6.5K traces. However, time domain and frequency domain correlational EM attack is unable to break AES 256 even with 20 million traces. This is comparison with existing state of the art. Our solution is very low area and low power overhead. It has some performance trade-off, but the operating region we are operating has very less performance trade-off. And also our TVLA result shows no leakage until 6 million phrases. Now I will summarize the key outcomes. This is the first countermeasure to enable inherent variability of digital circuit by slewed clock. This is a low overhead, synthesizable, and generic countermeasure. Clock slewing technique enhances the efficacy of system-level clock randomization technique. And as a part of future work, different low overhead slewing technique will be explored. Thank you.